Okay, welcome to the 15th lecture of EECE574, the graduate level probability and random processes. As usual, homework will be assigned, so be careful. And also our midterm is going to start soon, immediately after today's class meeting. I a little bit changed the time, so you need to upload, not submit, upload your solutions by next Tuesday before the Thursday before the class meeting. And it covers up to 2 days class meeting. Also, the handout for chapter 5 is updated, and you need to download it. Also, I uploaded the chapter 7 part of our graduate textbook, so there is no chapter 6 handout. Messages from instructor. Last time I talked about measurable goal. I said that the measurable goal setting is very important. And when you set the measurable goal, not to be too extreme, but keep increasing by pushing yourself slightly out of your comfortable zone. That is very important. Last time, we were covering a few sections of this chapter 5 about the operations of multiple random variables, and where I talked about orthonormal eigenvalue decomposition and Cholesky decomposition and factorization. So let me clarify a little bit of these things. Orthonormal and Cholesky. So last time, we've seen one important property of a correlation matrix. First, oops, what is this? So we have a real, possibly, matrix that is symmetric. And what? If you multiply some vector of length n before and after this matrix A, then it is always greater than or equal to 0, means what? Symmetric positive definiteness, right? So this is symmetric and this is positive definiteness. So if we have both of them, then what happens? Then A allows orthonormal eigenvalue decomposition, which means that you have orthogonal matrix V, and you have a diagonal matrix lambda that consists of all non-negative numbers. Here, positive semi-definiteness gives us non-negativity of eigenvalues. By the way, this decomposition exists. So this theorem is an existence theorem. Once I told you there are many theorems in mathematics related materials there, and also there is a small group of a subset of theorems that can be named as existence theorems. Existence theorems is very important because it provides us some conditions for some entity to exist. So in this case, this is called an orthonormal eigenvalue decomposition because we have, of course, we have this relation between the ith column vector and the ith eigenvalue. Got it? So under what condition? Real, symmetry, positive definiteness. Then what exists? Orthonormal eigenvalue decomposition exists. However, whenever we pass this existence check, what do we need? Uniqueness, right? So as graduate students, you must be now automatically have your idea. Okay, once I've checked existence, then next step is to check the uniqueness. Right? So is this unique? The answer is no, because simple permutation of eigenvalues will give you kind of permutation of your column vectors in V. So at least in that sense, this orthonormal eigen decomposition is not unique. You can permute, right? If you change the first eigenvalue and second eigenvalue, then your eigenvectors, first eigenvector and second eigenvector must change the position, right? So even in that sense, this is not unique. But if the orthonormal eigen decomposition is not unique, then which form of orthonormal eigen decomposition would be most useful? So here is one thing. I really prefer the case where I have some relation like this. So I prefer myself, and many researchers prefer reordering the eigenvalues in the decreasing order so that the largest eigenvalue appears as the first entry, first 1, 1 diagonal component of the diagonal matrix. Why? Why we do that? Because it's convenient, okay? And here, let me ask you another question. Then this form of very, very specific orthonormal eigen decomposition is unique? Again, it is not. Because sometimes you have same eigenvalues. The largest may not be unique, right? For example, just consider I sub n, the identity matrix of size n. Then what? Any orthogonal matrix, gives you what? This representation. What does that mean? Not unique. However, if they are distinct, then what happens? If they are distinct. So the theorem says, first, exists. Second, not unique, but you may have this form very convenient. Third, but that form is not unique, right? Yeah. Because of the algebraic multiplicity of the eigenvalues. So you may have some subspace where you can find any basis functions of the space to be used as the eigenvectors. Got it? However, anyway, this is very, very useful. So if they are distinct, but if distinct, then what? It's almost unique. Why almost? Because still you can change the sign. You can change the sign of the vector. So in that sense, right, it's not unique. Got it? So be careful, because sometimes the uniqueness is very, very important in your research. I suffered a lot from this uniqueness anyway. Okay, so now you have the orthonormal eigen value decomposition, and there is a complex valued version. So let me write it here. So you have now complex matrix A, and in that case, this becomes Hermitian symmetrical matrix, and also we have Hermitian transposition for all complex valued n by 1 vectors y. And also this orthogonal matrix thing becomes unitary matrix. Got it? However, still very interesting is this. Eigenvalues are all real. You learned in your engineering mathematics. Okay, eigenvalues are just real and also always non-negative. Got it? Again, orthonormal eigen decomposition exists, but not unique. Even though you have aligned eigenvalues, still due to the geometric multiplicity, you may not have the uniqueness. Even though you have distinct eigenvalues, still you have what? You can change not only the sign, but also the phase. For example, in this case, you can have something like this. You may introduce arbitrary phase shift. Still, you have the same thing. Why? Because as you've seen last time, this decomposition, let me write it down. Yeah, can be rewritten in this form, VI transpose. Similarly, for complex valued, you have VI Hermitian transpose. So if you replace V sub I with V sub I e to the j theta I, this one immediately cancels. So you have the same rank 1 matrix to be summed over. That's why you have more freedom when you have a complex values positive semi-definite matrix. Got it? Now, what about positive definiteness case? In that case, the only difference is this one. So if you have positive definiteness, then you need to drop this one. And of course, here you need to put all non-zero stuff. And you need to drop this and also drop that. Got it? So this is one of the most important theorem, existence theorem, you need to remember when you do any signal processing with random vectors. Got it? This is very, very important. And now, why this is very important for the signal processing of real random vectors? Because here goes some simple lemma. Two simple lemma. So given a random vector, whether it is real valued or complex valued, as we today learn, if you compute the correlation matrix, then it is what? It is always symmetrical and positive semi-definite. Got it? And it also holds for covariance matrix. Now, what about the Cholesky factorization? So here goes another theorem. Cholesky factorization, I prefer factorization because we write something as the product of factors. But however, as we never say eigenvalue factorization, we almost always say eigenvalue decomposition. These linear algebra guys love decomposition. So Cholesky decomposition is also very, very preferred term. And the condition is almost the same. A is a symmetrical matrix, real symmetrical matrix. And what was the notation for matrix semi-definiteness? I prefer this one. Here, the right-hand side is not just zero, it's kind of bold zero sub n to specifically say that this is an n by n zero all zero matrix. What was the definition of A greater than or equal to B? Yeah, A minus B is positive semi-definite. Anyway, so if we have these conditions, real, symmetrical, positive semi-definiteness, then what? There exists. So this theorem is also an existence theorem. And then there exists a lower triangular matrix L. Okay, this is a lower triangular. Such that what? A can be written as L transpose. Got it? Similarly, we can extend this one to complex valued, Hermitian symmetrical, positive semi-definiteness. In that case, we have LL Hermitian transposition. This is called Cholesky decomposition. And now we need to combine these linear algebra results with not only just real positive semi-definiteness of our covariance matrix, but the computer generation of random Gaussian random vectors. Before doing that, let's review what we studied last time. So in section 5.3, we learned the characteristic function. In section 5.2, we learned the real Gaussian random vector. These two can be linked very simply as this one. Any affine transformation over Gaussian random vector gives you a Gaussian random vector. Whether you increase the number of elements, or if you keep the number of elements, or you decrease the number of elements. Got it? Why is it true? Because if you use characteristic function, then everything is just clear. So given a Gaussian random vector, X with mu X and covariance matrix CXX, you have an affine transformation Y equals AX plus B. Then how can you show Y is a Gaussian random vector? Gaussian random vector with mean mu X plus covariance matrix A CX CX A transpose. How? As I just told you, use characteristic function. So you start from the characteristic function of the random vector Y, which is defined simply as, by definition, expectation of e to the j omega transpose Y. And simply you substitute Y with AX plus B, and you expand, and suddenly you have what? The characteristic function in the form of a Gaussian characteristic function with this mean that covariance. By the way, when I was an undergraduate student, I always got confused with that one. Is transpose here or there? But it's not that difficult, because if you remember the definition of covariance matrix, it is expectation of XX transpose after centering. So as you see here, AX are neighbors. So you have A and X, because this X is actually X transpose. Got it? Anyway, so it was very easy to show this. And then we moved on to section 5.4, where we have general nonlinear possibly transformation over general random vector to another random vector. And for that, we just relied on the Jacobi's method, because the CDF method is often very, how to say that, case by case. So it depends on the case. So our result was a kind of generalization of what? Generalization of this one when you have a density function of X. Then you remember the density function of Y. I asked you to specifically memorize this one because it can be your mental model for any transformation of a random vector to another random vector. So here you have the absolute value of this A in the denominator. And then you write the density function of X, because that is the purpose, right? You want to find the density of Y in terms of density of X. But here, the argument of the density function must have the same unit as X, right? So here, what is X? X is simply y minus b divided by a. So this gives you an idea what would be the form of the result in that case. So there we have n-dimensional random vector x, and temporarily we consider n-dimensional, the same dimensional random vector y, but general nonlinear transformation. Then what do we have? The result was quite interesting. The output, right, PDF, is the summation of the PDF of x. And we need to inverse, right? We need the inverse mapping. So let me see. Let's write in this way. Inverse mapping. Let's call G is the transformation function, vector valued function. And then here, what do we have? We must have something similar to the scaling factor A. And let's see, what is that? That is actually locally, if we consider very locally, is the matrix A that provides us the best affine approximation of function g at specific x0, right? So if the transformation function g is smooth enough, then locally, very locally, it can be always well approximated by an affine function, right? That is the idea of entire calculus, right? Very, very locally in the infinitesimally small area. Every function, every smooth enough function is an affine function. So you need to just find out this one. And what is that? Actually, that is the Jacobian matrix. So here goes the Jacobian matrix derived from G by partial differentiation. So by the way, we need that. So let me just write J, and we need some index because we may have non-one-to-one correspondence between x and y for general mapping x. That's why we have summation. Got it? So this is the result. And what is J? J is the Jacobian matrix. And what is, by the way, here we must have determinant. But sometimes determinant is just denoted by the kind of absolute value sign. So sometimes you have absolute something. But this second one, inner one, means determinant. Got it? The outer one means absolute value, because this mapping itself may have negative determinant, this matrix, Jacobian matrix. So our Jacobi's method involves computing Jacobian matrix and finding the Jacobian determinant and taking the absolute value at that specific point of x. Got it? Now, we've checked the cases where the input and output of vector-to-vector mapping does not have the same dimension or size. If the output is smaller, the situation is very simple. You just put arbitrary variables and marginalize. If the output is larger, then in the input side, you can assign arbitrary variables. That is the method, okay? And then we compare this characteristic function method and the this Jacobi's method for Gaussian case. We must have the same result, right? However, in our Jacobi's method, we start with our PDF. So this Jacobi's approach has a serious problem. When we try to generalize, when we have transformation of Gaussian to another Gaussian with longer vector, because in that case, our new covariance matrix, this one, AX transpose A times covariance of X times A transpose becomes non-invertible matrix, right? As you learned in linear algebra. Even though you have positive definite symmetric covariance matrix for X, if your A matrix is a tall matrix, then what do you have? You have singular covariance matrix that has some zero eigenvalues. So in this 5.5, we only consider, our textbook only considers the case where the X has positive definite covariance matrix, and our transformation matrix for a fine transformation, capital A, is what? A full-length square matrix. Of course, it could be a kind of wide matrix that gives a full-length wide matrix, but anyway, full-length matrix. So to make everything simple, let's just consider the same dimension and full length. In that case, we have the same result for the density. And what was the density function after transformation? As you expect, the mean is converted to this one, and the covariance matrix is given that one, okay? So we've covered and kind of combined and compared the different approaches, and then move to the second last topic of computer generation of multiple random variables. Actually, this has become very, very important these days. When I was a graduate student, it was not that important, except the generation of Gaussian random vectors. However, because of the use of MATLAB or other things, it was not a non-problem. However, these days, we have generative AI models that actually generates the outcomes of random numbers, random vectors, random images, or some conditional images. For example, if you use ChatGPT or Gemini to kind of trim your thesis, one paragraph of thesis, what would be the output? It's a kind of conditional random number generator given your original paragraph. And this conditional density function of mapping from input to output is determined by your script and also input, right? For example, like, please correct the grammatical errors. And then you put your paragraph. Then this is kind of random character generator. Got it? So this computer generation of multiple random variables has become very, very important these days. But let's stick to our classical problem first. So we've done what? Okay, something is not correct. Okay, let me delete this part, right? We've already covered that. So this is still a review part. So for the one-dimensional Gaussian, what was the classical method? We used uniform random number generator and just use what? The inverse CDF or percentile function to generate continuous or even discrete random variable. The problem of Gaussian case is that its CDF does not have a closed form. So its inverse also does not have a closed form. Of course, MATLAB provides us. But long ago, people did not have MATLAB. At that time, what did they do? And it was quite interesting. The idea was like this. It started from simple lemma. Suppose you have a two-dimensional Gaussian random vector with zero mean and unit variance. And then they considered what? Coordinate transformation. So they have now the distance from the origin and the arctangent 2, that is the angle, right? Exact angle of this number. Then they have shown that they are independent random variables when we have what? We have this condition. Zero mean, same variance. Actually, the uniqueness is not that important as far as they have the same variance. So, so they are independent, R and theta are independent. And what is R? This is a Rayleigh random variable. And this is what? Amazingly uniform, continuous uniform on 0 to 2 pi. By the way, one of the interesting results in one-dimensional random variable is that a Rayleigh random variable, when squared, becomes exponential random variable. So suppose you want to generate a Rayleigh random variable. What do you need to do? You generate an exponential random variable and take the positive square root. That is the idea of this two Gaussian random variable generated at the same time. So what do they do is very simple. They generate an exponential random variable and take the square root. And they generate a uniform random variable from 0 to 2 pi. And then from this to that, what do you have? x1 equals r cosine theta, and x2 equals r sine theta. So they plug in r and theta to have what? Zero mean, unit variance, Gaussian random variables. What does that mean? What does this mean? They are independent and identically distributed Gaussian. So we don't need non-closed form CDF because exponential random variable have closed form CDF. Uniform random variable does not need any mapping because you just multiply 2 pi to uniform random number. That is what you have seen, even though I just skipped very quickly. So this is the idea. See that? As you see, this generates when x is uniform. This generates an exponential random variable. So square root of exponential becomes Rayleigh. And here you multiply 2 pi to uniform x2. By the way, why this is x1 and x2? Okay. Yeah, anyway. So it must be like, okay, let's keep this u, okay? Because it's very confusing. U. Got it? So you have two uniform, independent uniform random variables, and you have x1 and x2. Got it? Then this result becomes the same as what I've just shown. So generating zero mean IID Gaussian is very easy. Generating multiple IID Gaussian, you just need to repeat this procedure. And if you have odd number, just drop 1. So generating, this gives us a method to generating a Gaussian zero mean unit variance IID Gaussian random vector, right? So you can generate this one very easily without relying on strange inverse CDF of Gaussian. Now, we want to generate a general Gaussian random vector. What can we do? We already have seen in our previous review that an affine transformation may work. So what do? We need to find some affine transformation that gives us what? This as what? A mu x plus b and what? A c x x a transpose. Now, what is mu x? Mu x is 0, so we don't need that, right? So here we've already found that this needs to be mu sub y, our desired mean vector of the output. And what about this part? We want to find A such that the desired covariance matrix equals A covariance matrix times A, where CXX is identity matrix. So we have this one. It looks like, very like Cholesky factorization. However, we don't know yet whether such a low rank approximation exists or not. But we've already seen from the linear algebra review that if we have a symmetric positive semi-definite matrix, then there exists a low triangular matrix that allows us this form. So we are done if we apply Cholesky factorization or decomposition. So let me write the block diagram. What you need to do is that you apply this IID Gaussian random vector. Let me be more specific. And you multiply the low triangular matrix from your Cholesky factorization to vector x and add your desired mean vector. Then what do you have? You have output Lx plus mu y that exactly have your desired mean vector and the covariance matrix. Another way is you apply square root of the square root of the lambda. So it's like you find this matrix, right? By the way, lambda square root means that you take the positive square roots of the eigenvalues in the diagonal, and then you add. Sometimes this thing is written as the square root of y. Here, I intentionally used y tilde because even though two outputs have the same probabilistic distribution, actually, given the same realization of x, of course, they generate different outputs, right? Be careful. These two outputs are not the same. Got it? Unless this one is same as that one, but it's not likely. Got it? Let me see. Yeah, is it? Yeah, we can also have other form like just the V lambda transpose. We don't need that actually. Either this one also works, as you can find. Okay. Yeah. Anyway, so this is a special case of Cholesky decomposition of our desired output. See that? Desired covariance matrix decomposed into AA transpose, and A is a lower triangular matrix. So probably I better write in this way. So I will update that next time. Okay. And this is a little bit interesting because see that whenever you have a lower triangular or upper triangular matrix in your linear algebra, it's like something similar to so-called back substitution in Gauss elimination. So for example, suppose you have L times X plus B to be used as Y. And just imagine that this is a lower triangular matrix. What does that mean? So you have generated a zero mean IID Gaussian. You have X1. That is just scaled. Sorry about that. So you have column vectors. So you have column vectors in L. So last column has just at most one non-zero component, right? And this one has what? All first entry is 0. So what is y sub 1? Y sub 1 is just this value times x1. x1 scaled, right? But last one is all x1, x2 weighted by this thing. Am I right? So in that way, you can easily see that it's kind of substitution. You use x1 and generate. And then for the second one, you generate x2 and you use x1 and x2, right? So this one, y, has what? The first entry affected by x1. Second entry, x1 and x2. Third entry, x1, x2, x3. Last one, all of x. This gives us some interesting idea. What kind of idea? That is the topic of today's coverage. And so here, do you remember this one? This is called the chain rule for two jointly distributed random variables. And it's obvious now that you have two identically the same, but in different forms, represent decomposition. Unconditional x times conditional y, or unconditional y times conditional x. But does this provide you an idea how to generate a jointly distributed random vector? That is my question. Can we use this chain rule in generating two dependent random variables in general? So let's see. So just consider the case where you have a single random vector generator that generates x and y at the same time. And also consider this one. You have a random vector generator. You generate x. Can you do that? Yes. How? Use the percentile function or inverse EDF, right? You use uniform random number u, and here you use the percentile function of the inverse EDF, right? Now you have generated x. What can you do to generate y? That exactly follows that one. How? And now let's go back to our idea of 2D histogram. Okay? What is a 2D histogram in this case? 2D histogram is nothing but a processed version of 2D scatter plot. So suppose you have some desired scatter plot of x and y. What you need to do is that you put something here so that when your xy pair is dotted here, you have this scatter plot. But you already have generated x, some value. So suppose your random number generator for x has given you some x0. What does that mean? What do you need to do as if you have that one? Just find x0 here. And of course, whenever we talked about 2D scatter plot histogram, we have a small streak, right? So for y, you have what? Sorry. You have to generate dots that falls in this area following what? The conditional density of y given x evaluated at what? x0. Now, suppose you can find the inverse EDF of that one. then what do? So what you do is that you have another random number generator. And here, this is the inverse CDF of the conditional distribution of Y. Evaluated at what? Sorry. Evaluated at X. So this is not a random variable. Actually, I just want to emphasize that you need to have the family of conditional CDFs, inverse CDFs, because depending on the realization, right, you have to select different inverse CDF. However, theoretically, in theory, you can do that, right? So you generate X first, and then you generate Y. And actually, I'd rather not just to put conditional sign. So you take this X and that Y, and that is exactly same as you take these two XY. Be careful. I'm not saying that when you generate a pair of XY, you get some two-dimensional point or vector, and that appears exactly the same. I'm not saying that. What I'm saying that this method gives you exactly the same joint PDF. So as a random vector generator, they function in the same way. They are mathematically equivalent. So do you see the power of viewing any joint density as a 2D scatter plot? That is very important. I didn't realize when I was a graduate student, because at that time, this was not that important. But as a professor, I have to keep learning, right? And suddenly, those generative models and those machine learning models challenged me. Like, how can we generate a random vector based on our experience, so-called training data? So for example, we don't know the exact model of some source, but it generates a random vector. Now, we have a lot of data, like these dots in the scatter plot. And our task is not just the classical task was to model this one using Gaussian mixture or some simple model. But these days, we are just asked to use, usually, neural net-based some strange mapper that, if we say generate, like Nara, as you know, those EECE favors, right? It's related to golden egg generating duck, right? Nara. Then we must have some output that follow very similar distribution as that one. This is what we want, right? Depending on our some training data. Like we train a lot of Van Gogh's painting to some model, and then you take a picture in PostDec campus and say, give that, and that machine learning model generates something like Starry Night at PostDec, right? That is what's going on these days. So you have to understand how this simple chain rule and combined with your understanding of the joint density as a limit of 2D histogram, you understand almost everything. Now, let's generalize to what? 1, 2, then many, right? 하나, 둘, 많다 in Korean, right? So let's consider generation of general random vector. Of course, in this case, we assume that we know this distribution, joint distribution, but in machine learning case, that is even provided by the training data. But anyway, we can always do what? Factorization using chain rule. So once you generate x1, then you generate x2 given x1, and you generate x3 given x1 and x2. In this way, you can use uniform random number generator that is converted to a scalar random vector, which means a random variable. So at one time, you can generate a random variable. Now, random variable is sequentially generated. You first generate x1, then x2, x3. Of course, you have how many? N factorial reordering. So as you wish, you can generate x3 first, and then x million, and then x2, right? And also, you can do this. You partition the random vector into several random vectors, not just random variable, because sometimes you can generate the random vector, part of it directly. For example, you have a vector x, and it seems that the first million entries are jointly Gaussian. Then just use Gaussian random number generator, and then you generate a part of the random vector, and then part of the random vector. In this way, you can generate, in theory, any jointly distributed random variables. Got it? So that is my message. Okay, so we are done with this fifth one. And let's move to the section 8, complex random variables part. This part is revised, so you need to download it again. I combined the undergraduate lecture note and last year's lecture note. It took me a lot of time. So please. So let's first start with one complex random variable. As you will see, I love this 1, 2, and many, okay? So let's start from one complex valued random variable. This is sometimes called complex random variable or complex valued random variable, in order to be more specific, but complex random variable is okay. So we have let me draw. We have a random number generator. Now it generates a complex number that has real part and imaginary part. Now be careful. The real part is very simple, but imaginary part actually is what? Imaginary part is also real. So you have real of z plus j times imaginary of z. Here, j is the square root of -1. Got it? So whenever you generate a complex random variable, you have what? A point in this two-dimensional plane or z-plane, right? So does it remind you something you already know? Yes, actually, this is a simple, right? A notation of a two-dimensional random vector. So one complex random variable is simply equivalent to two jointly distributed real random variables. We just introduce simple notation like this. See that? Complex random variable is actually consists of two jointly distributed real random variables. And we just use simple this addition using the square root of -1. That's all. We need two-dimensional scatter plot, two-dimensional histogram, the limit of it. But be careful. When we have the density function of complex random variable, what do you want to do? Theoretically, you have to write this way, real part of z, because this argument g, let me write it again. So this confused me a lot, so I want to be careful. So actually, even though you want to write your density function as a single argument function, actually, it is not a single argument function. It is a two argument function, like this, right? Because a complex random variable is equivalent to a two-dimensional random vector. However, in some cases, not every case, in some cases, you can very simply find the density in terms of z, okay, without talking about the real and imaginary parts. However, those cases are very, very special. Be careful, okay? So we really need these ideas, right? See that? This is exactly what we have seen for the generation of two jointly distributed random variables. We have an underlying probability space that models a random experiment generation. Outcome is S, and you have two measurable functions named X and Y, and now you have two outputs or mapping of S. And then what? You multiply J and combine these together to have a complex number. That is this generator. Got it? So as I told you, the X is the real part and Y is the imaginary part, so that we have this interesting notation using conjugation operation. This conjugation operation is very strange, as you've seen in engineering mathematics. Probably you remember, given a complex valued function of a complex number, right? So you map z into f in your, so confer. Suppose you have a function from c into c. What does that mean? Actually, your function is what? Real part of z, imaginary part of z, and real part of z and imaginary part of z. That is the way to understand your function f of z, right? So you have two functions of two variables. That was your function. And at that time, in order for this function to be well or fine approximated, then what was the required condition? You already forgot, right? The function must be analytic. What does that mean? It must satisfy Cauchy-Riemann equations, right? Anyway, so there, what is important is that this f must be well approximated by what? Locally, by what? Again and again. Locally by an affine function. That does not involve conjugate of z, because this conjugate, when you do some approximation, if you have this conjugation, you are doomed. You cannot have a smooth thing. Anyway, so this conjugation makes us have a headache. However, if you use it properly, it's very, very useful like this. So whenever you want to handle real part operation and imaginary part operation, you just remember this one. You conjugate, take the conjugate, and sum and divide, then you get the real part and imaginary part. This is very important when you handle almost everything, especially when you want to generalize this to random vectors. For example, if you put underlines, then you have the same thing for the complex valued random vectors. Anyway, we can easily consider the random vector. Now, what about complex Gaussian random vector? What about complex Gaussian? Complex random variable is Gaussian. Now, let's go back to complex random variable is Gaussian. Okay, what does that mean? As I just told you, we have two real random variables. What would be our best definition? Yes, these real and imaginary parts are jointly Gaussian. real random variables. Got it? So when we have a two-dimensional scatter plot, we have that beautiful two-dimensional bell curve. Got it? In that case, that is called a complex Gaussian random variable. Now, this is already done, right? Real part of Z and image part of Z. What would be the density function in terms of Z only? Is it possible? Unfortunately, it's not possible. You must be careful, okay? We cannot have complex Gaussian density in a simple sum form in terms of Z only. As I just told you, we always need Z conjugate in general. However, under certain condition, we have very interesting result. Before we talk about that, let's introduce the moments of a complex random variable. And that is very simple because this, our new definition must be compatible with our moment definitions for 2D random vector. So here, mean of Z is related to what? Mean vector of xy. What about variance? This is strange. So we subtract the mean of Z and take the modulus or absolute value squared. And here, when I first saw that, I really got angry because the professor just said conjugation is very important, but he ignored it. You will see. Because I just thought that, what about just squaring it? And professor said that that's not variance. Actually, that is variance. Later, I knew that. The professor didn't know. And here goes so-called the pseudo variance or complementary variance. It has just a square. Why do we need both of them? Because the story is like this. If you just consider this modulus squared, you cannot have all the information of second order moments of x and y. You need both of them. And it can be easily shown that by subtracting this thing, adding this thing, or taking the real parts, you can find the moments of x, moment of y, and cross correlation. But this alone does not provide these three things. Because see that this one has only what? Two real numbers, real part and imaginary part. We have three things to be resolved. And we have actually here three more, but they are related and gives you these three things. The easiest way is just replace Z with x plus jy, and you will see why I talk about this one. By the way, variance of Z as it is defined is the real part, right, squared plus imaginary part squared. So what do you see? You don't have cross correlation. So this does not give you cross correlation information. However, complementary variance, as you see here, not only gives you what? The subtraction of two variances, but also the covariance. Now, as I just told you, see that? Variance is real, as you see. No imaginary part. And variances are summed. So even you cannot distinguish these two. However, see that here, the real part is the difference between variance of x and y. So if you add these two real parts, if you add real parts and divide by 2, you have variance of real part. If you subtract and divide by 2, then you have the variance of imaginary part. You take the imaginary part and divide by 2, then you have the covariance. Got it? That's why you need variance and complementary variance to have all the second order moments. Got it? Same for the correlation and yeah, same thing. So this is what I wanted to say. Now, here goes something interesting because in many applications, not all, in many applications, we have density function just which can be written without explicitly involving conjugation. So we do not need real pattern imagement. Here, this is the case. Probably you've seen this in your communications course. And at the first glance, you said that, hey, professor had a mistake. There must be square root and 2 here, and also 2. No, okay? This is different. You have complex variable z, and this is not just the absolute value of a real number. This is the absolute value of a complex number or modulus of complex number. But this density is not general complex Gaussian random variables density. It's a very special case density. It's so-called proper complex Gaussian density. But before we talk about that, we need to define the properness of complex random variable or after generalization vector. And here goes very interesting definition. In some cases, complementary variance becomes 0. What does that mean? It means, as you see here, this is 0, means real part is 0. What does that mean? The variance of the real part of z and imaginary part of z are the same. Second, covariance is 0. What does that mean? They are uncorrelated and having the same variance. Got it? Now, why this propriety important? Because if we combine Gaussianity and properness, then we have very interesting density for Gaussian, complex Gaussian, proper complex Gaussian. So this means that the real part and imaginary part has the same variance. And in Gaussian case, uncorrelatedness means independence. So real and imaginary parts are independent. So what does that mean? This is actually, as you see, what? In the two-dimensional scatter plot plane or complex z-plane, what? You have some mu z, and around that, you have circularly symmetric scatter plot. So this is proper complex case. But as you've seen already, general 2D Gaussian, we have ellipses for the level sets, right? So very special case of 2D Gaussian is called proper complex Gaussian variable. And here, this sigma square is the variance of z. So actually, the real part has half of the variance of z, and the imaginary part also has the half of the variance of z. Got it? And they are independent, circular symmetry. Got it? This is what I just emphasized. By the way, this propriety and circularity is a little bit different. See that here we define circular random variable. And circular means, it depends on the definition of many researchers, but suppose you have a complex random variable z and its transformation by multiplying e to the j theta with some arbitrary theta. Now, if these two have the same PDF, then it's called circular. Then what does this mean in Gaussian case? Suppose you have zero mean proper complex Gaussian case. In that case, this propriety and circularity are the same. However, according to this definition, if you have proper complex Gaussian density that has circular symmetry around some non-zero complex number mu sub 0, it's not circular because if you rotate that, it does not give you the same density. However, some people say that, hey, what I want is that after I subtract the mean, then circular. So be careful. When some people say complex random variable is circular, some people talk about real circular thing around the origin. But some people mean that after centralization. Got it? So be careful. But anyway, so in Gaussian case, by the way, according to this definition, circularity is stronger than propriety because it requires zero mean, right? So in that sense, circularity is a special, stronger definition than propriety. However, this is no longer true when you have a random vector. Anyway, here goes some results. You read it. Expected value of real or complex valued function g that admits complex random variable z. Then what do you do? If you want to compute the expected value of g of z, it's not that difficult because expectation is a linear operator and a function, whether it is complex valued or real valued, can be rewritten as a summation of two real functions with one j, right? So this is your definition. Just simple, too simple to talk about. Now, let's consider two complex random variables. Then what? Actually, this is nothing but what? 4 jointly distributed real random variables. So nothing new. If you want, but be careful. When you talk about independence between two complex random variables, actually, 2 of the random variables are independent of 2 of the other random variables. What I mean is that 4 of the real random variables may not be independent, but after you group 2 by 2, then they are independent. Correlation is defined with conjugation. Sometimes the order is important, and people love to put conjugation on the right side. And actually, I prefer that. Okay? Complementary case, you don't need conjugation. Covariance defined similarly. So probably I want to modify that one. Yeah, this is consistent to my philosophy. But anyway.
Dr. Joe, it is time to wrap up.
Okay, I have 1 minute, but a lot to cover for your exam. Just a second. Okay, so pseudo-variance, complementary covariance, uncorrelated, orthogonal, defined similarly. Then we move to random vector case. We need 5 more minutes. So here we have real part vector and imaginary part vector. But this is just simply you have 2 jointly distributed real random vectors of same length. That's it, right? So you have mean, correlation. See that? You have the Hermitian transposition on the right side. That's why I want to keep consistent. So covariance, pseudo-correlation, pseudo-covariance. And again, the propriety of a complex random vector is defined in terms of the complementary covariance matrix. If that matrix is a 0 matrix, we call it proper. What if we have proper complex Gaussian? In that case, we have very, very interesting form like this, very compact. Here, we don't have square root because we have all real parts and imaginary parts that have square root, and squared is removing that square root. So pi to the n, here n means the length of z, each part of real and Gaussian of length n. You have determinant of z. You don't have absolute value because correlation or covariance matrix is positive semi-definite. So your determinant is always non-negative. And we assume it's invertible. So this is real positive, right? And we have exponential function. And then the exponent, we don't need 1/2. Instead of something over sigma square, we have the covariance matrix. Got it? And here we have a quadratic form that involves Hermitian transposition. Got it? And one good thing is that if we have propriety for Gaussian random vector, each component, so z consists of z1, z2, z3, interestingly, each entry is proper. You can easily show that if you have a proper Gaussian random vector, any affine transformation gives you a proper complex Gaussian random vector. And the simplest one is removing all the entries. So each one is proper complex Gaussian. So real and imaginary parts have the same variance and they are uncorrelated. Same. But these two components may have correlation. But under the assumption of propriety, they have zero complementary correlation, covariance. Right? The last topic is circularity of a complex random vector. It is similarly defined as that one. And you can now show that circularity is much stronger than propriety. Okay? Because propriety is only about what? Second order moments, not distribution, right? But this circularity is about the distribution, not just the second order moments. In Gaussian case, they may have relation, okay? In some special distribution that has circularity or symmetric or rotational symmetry with respect to its mean, then these two definitions may become equivalent. However, in general, they are different. Okay, we have done our chapter. Actually, this 5.7 sampling and some limit theorems will be covered with this new handout, chapter 7 of our Populist textbook. Of course, it covers what we already have studied. So I will very quickly review this one and move directly to what? Directly to that one. These three sections are related to what? This section, sampling and some limit theorems. As you see, sampling and some limit theorems. So that's all for today's class meeting, and good luck on your exam.